Good morning, ladies and gentlemen. My name is Johannes Mbiza. I'll be conducting a lesson on materials technology for level 3 on topic number 4, which is material testing. So today's lesson I will be doing the tensile test, which I will look at the outcomes, which it will be, at the end of the day, we're supposed to calculate the strength of the material, which will be the ultimate strength. And we also have to know how to calculate the yield point, the percentage elongation of that material, and also the percentage reduction of area. So the lesson of the day today, it will be more based on this diagram, which I'm going to explain the stress and strain of the material, or how the material behaves under the influence of pressure. Where I will start with point number A. This is the actual drawing, or the actual material, in actual way that I have a material initially at this stage. So this page is coming from topic number 4, material testing on your prescribed textbook. So before the material reaches point number A, the material has to go under a certain influence of pressure, or under the characteristics of pressure, which you have in a linear pattern. That line, which you can also calculate the gradient, and the gradient of that line, which is going to result to Young's modulus. So Young's modulus, which will be E, is equals to the stress over the strain, whereby we use the Greek letters, which is the stress, which is the sigma, and then the strain, which is coming from the epsilon. So for material to reach to point number A, can you all see? Yes. So for material to reach to point A, it's when the material is still at its elastic state. So when it reaches at point number A, when you stretch the material, or when you pull the material, or under elongation, or under deformation, because the material has to deform as it will be pulled from 0 point to point number A. And then after that plastic elastic deformation, after I have stretched that material, it's no longer going to stretch, it's going to be permanently set. So it's going to go from elastic stage to plastic region. So as it reaches point number B, the point number B, which will be the yield point. So that will be our yield point. So when you reach point number B, it is when now the material has permanently set. In other words, it can't go back to its original position. It can only go back to its original position if it's from 0 to A. But if it has passed the point A, it can't go back to its original position. So that means now from that region to go to point B, it will be now transforming, or it will be in a deformation of reaching the point where it's going to be in a plastic region. So I'm not going to concentrate much more on point number C, because that is the lowest yield point, and D, which will be the highest yield point. The region that I'm going to be talking about is this point of point E. That is where the ultimate, or the maximum, load will be experienced. Right at that point, at point number E, that is when this necking is starting to begin. That neck starts to transform, or starts to happen, which will be at point number E. In another words, now you are in a plastic deformation. So as you continue to apply the load, or as you continue to increase that load, the material itself is no longer going to be able to handle that load. What I mean by that, I mean that the material will go under this influence. So it will be at point number A and at point number D. As you continue to pull or to apply the load, it's going to reach a certain point where it's going to fracture. And then it's going to be able to fracture. And then with the calculation purpose, you must be able to calculate where you're going to take the measurement. So you're going to originally take measurement of the original length, which will be from that point A and point number B. And then after that, as you are applying the load, it's going to go under this change or under this deformation, whereby you can see that now it has changed and went to plastic deformation. As it continues to, in a plastic deformation, it's going to fracture. And when it fractures now, it can't be able to handle the load anymore. Then the material will fail. So we have the percentage or the stress that we allow the material to stretch, especially from the beginning, which will be that stress point. When I refer to your textbook, on page 161, it says here on this paragraph, that's the only paragraph I want to concentrate on. That says that for metals which do not have a clearly defined yield point, if the yield point of that material is not clearly defined, then we have the proof stress are used. Proof stress is the amount of stress that when applied and then removed, reduces a permanent stretch equals to a specified percentage of the gauge length. The percentage usually specified are from 0,1, which you can, when you convert that, it will be 0,001. In that, what I'm referring to when the material starts at the initial point. At that particular point, you can have it right at the beginning there, which is going to be 0,001. That will be parallel to the stress and strain of yours. So in another words, that material can only stretch 1%, and after that it will go to the plastic deformation. Yeah, can you? Yes, so this is how the material will behave. If we have that 0,1, 0,2, and 0,5, that is the allowable stress. So the material will start at the beginning at original length, the changing length, which will give us the strain. The changing length, which is going to be the changing length over the original length, which will give us the strain. As you can see that I will be starting right there. I will take measurement from that point and then I will apply force. As I apply force, the material will start to deform from point number 1 to point number 2 to point number 3 as it goes along, and the maximum point where now the material will start to nag, and then the material can't handle the load anymore. It can't handle the load anymore, and then it will fail. At failure point, then we combine part A and part B to get the original final length. What will be the final length of that material? And it will be able to help us to calculate or do the calculation if we do understand that the material will be starting from there at elastic region and then up until plastic deformation. That is how the material will go along. So I have a quick example that I want us to go through. That will be in relation to the information that I've just displayed. I'm going to do a typical example which is coming from one of the questions in the book. So the information given is that from the original length I have 50 millimeters and the original area is equals to 200 millimeters squared. Then the material is going to go under deformation with 0.2% stress point, and to that 0.2% stress point, the force that will be experienced is equals to 98,000 Newton at a length of 50,23. So for me to calculate the stress yield, I will need force over area, which will be 98,000 divided by 200 mm squared, and the force will be calculated in newtons, so that will result to 490 megapascals. So that will be my stress at the yield point. And then for me, after that, I have to go and calculate the strain, which is equals to the change in length over the original length, which is going to be, so I have the length of 50,23 from 50 millimeters. So it's going to be 50,23 minus 50 divided by the original length, which is equals to 50, and that will result to 0.0046. So there is no SI unit, it's unitless. So the formula actually is right equivalent to final length minus original length, all divided by original length. And then that, because I do have the two, now I can be able to calculate modulus of elasticity. Modulus of elasticity is equals to the stress divided by the strain. So I do have the stress at yield point, and I do have the stress, the strain at yield point. But now the effect is that I do have that which is going to be 490 megapascals divided by 0.0046, and that will give me, if I punch that, so that is going to be 490 divided by exponent 10 exponent 6 divided by 0.0046, and 490 divided by 0.0046, and that will give me 106,521,7391 megapascals. So if I divide that by 1,000, I will get that is equals to 106,521 gigapascals. So my strain, it has been influenced by that 0.2%, which I did include on my calculations so that I can be able to get that 0.046. So the total answer, or the total strain modulus of elasticity, is equals to 106,521 gigapascals. That is how the material will, the stiffness of the material at the end of the day. So the material is stiff up until that particular region. If it goes beyond that region, then the material will fail. Thank you.